As you can see from the title of this lesson, this is a tutorial on solving gas stoichiometry problems at non-STP conditions. To this point, we have done various gas problems where we were using molar mass, density, volumes, plain old-fashioned mass, and now molar volume to get different things about gases in a real-life setting. The perfect real-life setting is where we are not held to a specific set of conditions at temperature and pressure known as STP, standard temperature and pressure. In class we solved two problems that let us show how to do this, and we will do that here as well. But a quick overview of how it works is it's a mixture of what we've done in the last chapter with gas laws and what we've done in this chapter, which are a series of stoichiometry or bracket type problems. If you go to the fourth handout, which is titled Gas Stoichiometry Not at STP, that you can see the two questions that we're going to solve here. The first one says, what is the molar mass of a gas if it has a mass of 1.25 grams and takes up a volume of 350.0 milliliters at 20 degrees Celsius and 750 mmHg. If we're going to solve a problem like this, we try to attack it the same way as we have all the others. List what we know, list what we're trying to find. What I know is I've got 1.25 grams of a gas. I don't know its identity. I know that vol is 350 milliliters. I know that those 350 milliliters exist at a certain set of conditions, that is 20.0 degrees Celsius and 750.0 millimeters of mercury. Then we list what we're trying to find. The question says, what is the molar mass of the gas? Which again means we are looking for the units of grams per mole. When we did these problems earlier, we had a case where we had multiple numbers, and we always said we needed to stack the numbers in some fashion. Now that I have four different numbers, how is it that I'm going to decide how to stack them? You only stack two of these numbers. One of the two, if possible, would like to have units that you see in the answer. So because there's grams in the answer, I'm going to put 1.25 grams in the numerator. You'll soon learn that there are a variety of ways to do the rest, including what we will learn this upcoming latter half of the chapter, right, where I could take these three pieces of information and I could get them all separately and divide. But if I wanted to do it in a one-step bracket problem, I will put milliliters on the bottom. Notice, I'm not going to put the 350 in. Here is why. If I want to get to grams per mole, I need to cancel milliliters from the bottom, change it into liters. That's a 1,000 to 1 ratio. Then, I'll put liters on the top and put what I want there, which is moles, 1 to 22.414. However, this is only true at STP, and my volume originally is currently not there. So if I am going to be able to plug in, the milliliters that I plug in here have to be the milliliters at STP. So this creates a scenario where I have an initial volume of 350.0 milliliters. I have an initial temperature of 20.0 degrees Celsius. I have an initial pressure of 750.0 mmHg. I want to know about the volume of a gas at STP, standard temperature pressure. STP, if you remember, is 0 degrees Celsius or 273.15 Kelvin, and 1 atmosphere or any conversion of that, 760.00 millimeters of mercury. So you can see this is shaping up to be a combined gas law from the last chapter. If you remember, the combined gas law says P1 V1 T2 equals P2 V2 T1. I would like to solve for V2, so I divide away P2 times T1. These cancel, leading me to say that V2 is equal to P1 V1 T2 over P2 T1. Before I can plug that in, I always make sure that my units match and my temperature is in Kelvin. If you take a look, pressure, millimeters of mercury matches. Temperature, degrees Celsius in Kelvin. It doesn't match, nor are they both in Kelvin. So I'm going to change the degrees Celsius into Kelvin by adding 273.15. This is only going to get me a number of 293.2 due to sig figs. I'm adding and subtracting, so I care about places past the decimal point. This goes one place past. 273.15 goes two past. Therefore, my answer can only go one past. Now that I have units that match in temp and Kelvin, I'm able to plug in and get myself a volume. Pressure 1, 750.0 mmHg. Volume 1, 350.0 milliliters. Temperature 2, 273.15 Kelvin. Pressure 2, 760.00 mmHg. Temperature 1, 293.2 Kelvin. So we'll plug that into our calculator and get ourselves an answer. 750.0 times 350.0 times 273.15 divided by 760.00 divided by 293.2. If I take a look at my sig figs, I have 4 here, 4 here, 5 here, 5 here, 4 here, means 4 in my answer. So my calculator says 321.77. I will call that 321.8 milliliters. That milliliters is at STP because I am now able to plug it in to this problem. We are at standard temperature pressure. That's what we needed to use the 22.414. So now 350 milliliters at this condition only take up 321 mils at STP. We can plug in and finish our problem. 1.25 divided by 321.8 times 1,000 times 22.414. My calculator says 87.0649. I only get 3 sig figs, so I will call it 87.1 grams per mole. So the only difference between a gas problem at STP and not at STP is at STP we plug directly in and we only do brackets. If we are in non-STP conditions, you have to do some version of a combined gas law and this, right? Or what you will see in a later tutorial where you can do a problem using the ideal gas equation to get moles separately. Moving on to the second example. Number 2, or on this sheet number 11, says, what is the molar mass of a gas if it has a mass of 5.24 grams and occupies 14.8 liters at 46 mmHg and 29.0 degrees Celsius? I made these problems very similar, again, so that you can try to solve a problem that you don't know the answer to by comparing not the answer that you see from your notes, but the questions that you see. And that is why I tend to stress in class that you need to copy down the questions of these things as much as you do the answers. Having an answer without the question is like having a lock without a key. So we would do the same thing again. I would take what I know. It looks like I know I have 5.24 grams. Also tells me that that occupies 14.8 liters at 746 millimeters of mercury and 29.0 degrees Celsius. Once again, I'm looking for the molar mass for my question. So if you notice the similarities between these two, I'm given grams in both. I'm given a temperature in Celsius. I'm given a pressure in millimeters of mercury. I'm given a volume in liters and a volume in milliliters. The only main difference between these two is that I have a different unit of volume. So when I begin the problem, I'm going to try to mirror what happened over here. Over here, I started with my mass over my volume. We will do that as well. 5.24 grams over the volume, this time which is in liters. Then we set up our brackets. I converted liters to milliliters here, which I don't have to do because I'm in liters. So I can jump straight to this second bracket where we convert liters into moles using the 22.414. Again, this only holds true at STP, so I have to get my liters to be in standard and temperature, standard temperature pressure conditions. Again, that's going to lead us to use these three values in some type of combined gas law. Listing our conditions again, V1 would be 14.8 liters, T1, 29.0 degrees Celsius, P1, 746 mmHg. V2 is what I'm looking for. T2, standard temperature, 273.15 Kelvin. P2, standard pressure, 760.00 millimeters of mercury. Looks like a combined gas law again, which says P1 V1 T2 equals P2 V2 T1. Solving for V2 looks like P2 T1 gets divided on both sides, leading me to V2 equals P1 V1 T2 divided by P2 T1. Before I plug in, I must make sure that my units match and my temp is in Kelvin. Millimeters of mercury, Celsius, Kelvin. So I have to change my Celsius into Kelvin. Again, do that by adding 273. And if you take your 29.0 plus your 273.15, your calculator is going to tell you 302.15, but you can only write 302.2 K due to sig figures. Now my units match and my temp is in Kelvin, so I can plug in. Pressure 1, 746 mmHg. Volume 1, 14.8 liters. Temperature 2, 273.15 Kelvin. Pressure 2, 760.00 mmHg. And temperature 1, 302.2 Kelvin. Again, do the math on this. 746 times 14.8 times 273.15. divided by 760.00 divided by 302.2. Taking a look at your units, mmHg goes away, Kelvin goes away, leaving us with liters at STP conditions. And with 3 sig figs, that is a value of 13.1 liters. That is at STP, so I am allowed to plug it in up here and use the 22.414 liter conversion. Taking 5.24 divided by 13.1 times 22.414. The only unit that doesn't cancel are grams and moles. My calculator says 8.9756, but with only 3 sig figs, I have to call that 8.97 grams per mole. So here are 2 different problems at not STP conditions. Again, notice the main difference is you have to add a combined gas law problem, or as I said, you'll see in a later tutorial, an ideal gas equation problem to get yourself the pieces of information that you need to get the correct molar masses of these gases. I hope this helps out. If you're still struggling, please come in for some help.